We're live, everyone.
Welcome.
Welcome, coilies and callers. Hugo Bowne-Anderson here with Matt Rocklin, regulars, and our special guest of today, Deepak Cherian. Hey, Deepak.
Hey, Hugo.
How are you?
Doing great. I'm excited.
As are we. So I'd just like to welcome everyone. Oh, I've got my own audio coming back in with a 20-second lag.
You gotta hit the mute on the YouTube button. Here you go. There's various skills in live streaming, it turns out.
Okay. Sorry about that. I actually have it somewhere else. Could you lead, Matt, while I sort this out?
So I know Deepak as both an oceanographer, I want to say. He works at NCAR. He is also one of the lead maintainers of Xarray. And we often interact on Dask array issues or pull requests where he implements amazing fixes in Dask array. So I love Deepak. But today I get to hear more about his actual scientific work, which is fun. Do you want to briefly introduce yourself a bit more, maybe definitively than I just did?
And I'll ask people to introduce themselves in the chat as they join us as well. And I'm back and ready to roll now with less of me coming in. So yeah, please introduce yourself, Deepak.
Yeah, so my name is Deepak Cherian. I am a physical oceanographer, which means that I study the fluid dynamics and fluid physics of the oceans. I tend to work on somewhat regional problems. I've thought about the Indian Ocean, the Equatorial Pacific, and then today we'll look at the Eastern Tropical Pacific, so kind of a little more near the coast. I work at NCAR, which is the National Center for Atmospheric Research in Boulder, Colorado. NCAR is one of the US's big climate modeling centers. So today we're going to be looking at some ocean model output and see how I use Xarray, which is a cool package to make my life really simple.
So as an oceanographer, does that mean you're going into oceans and studying them? I don't think so. What does oceanography look like today?
So we do go into the oceans and study them. So before I got to NCAR, I was an observational oceanographer. So I was on a ship for like 30 days in the South China Sea. And then in the Western Pacific, we left out of Palau, which is a tiny tropical nation, making cool measurements in the typhoon track in the tropical Pacific, which is a lot of fun and entertaining. So that's so there's like a whole side of observational oceanography where you take ships to little points of the ocean, drop a bunch of instruments. You have autonomous instruments, robots, gliders flying around. We also have satellites up in space, looking down on the ocean, taking cool pictures and sending them back to us. We have autonomous floats. So these things are just floating around the ocean, going up and down, beaming back temperature, salinity, things like that. So, and then on top of that, you have modelers who solve finite difference equations, basically Newton's second law for fluid physics, also known as the Navier-Stokes equations. You specialize those for the Earth's oceans and solve them numerically.
So you simulate them at scale.
Sorry? So
you perform large scale simulations from the differential equations.
Yep. So you kind of specify, what the atmosphere is doing, the winds and stuff. You specify, in this case, things that come in at the boundaries. You integrate forward in time. You get like fields of temperature, salinity, 3 components of velocity. So in X, Y, and Z. And then, so this, these kind of ocean models, they're coded in Fortran. There's a new project that's trying to do them in Julia. But the stuff we look at today, it's Fortran models they have the capability to output enormous amounts of data to disk, which is where things like Dask come in. They make it easy for me to look at large data sets and large outputs from such models.
Great. I used to work with Navier-Stokes type stuff. This is a little tidbit, but I worked in biophysics. So it was slightly different. It was life at what we call life at low Reynolds number, right? Where viscosity reigns, which was a lot of fun to think about. So you mentioned Dask, which I want to jump into in a second. I just wanted to mention that Matt works on Dask, and we work at Coiled. We're building products to help data scientists use scalable clusters. And we have hosted deployments on the cloud. And if you want to check out our beta product at beta.coiled.io, that'd be awesome. And if you're enjoying this stream, please hit subscribe as well. All of that stuff aside, though, we're here to check out Dask and Xarray and physical oceanography with Deepak. But one thing I always want to ask at the start, and I asked Matt this, is could you tell me what Dask actually is?
And so I always deflect this question to our guest. So Deepak, what is Dask to you?
Dask to me is basically Dask array. So I work with usually 4-dimensional dense array datasets. And so Dask is a really nice way for me to deal with large 4-dimensional datasets, but in a very distributed manner. But to me, Dask is also the Dask dashboard or the lab extension. I spend a lot of time looking at it.
Cool. So, given that, should we jump in?
Sure.
Definitely. And I just want to say we've got a lot of people who've jumped in here. And I just want to say hi to Jesse from Insight. We've got someone from Monterey Bay from the Aquarium Research Institute. We have Guy Maskell, who's been currently wrestling exactly with Dask and Xarray. Alexis Kaminsky, who's a physical oceanographer at UW. Deepak says hi, of course. So we've got a lot of different interesting people in the proverbial room, and I just wanted to welcome everyone. So yeah, let's jump in.
Okay. So I have a notebook up on screen, and so hi coiled. Today we're going to talk about oceanography, Xarray, Dask, and the intersection of all those things, which is what I do. So I've started working on this new project, and it has a really cool motivation. So I decided we would start with that just to get everyone interested. We're looking at the Eastern tropical Pacific. So this down here is South America, that's Central America, and up there is Mexico. There are a bunch of coral reefs here. So these are locations of marine protected areas that have coral reefs. And the idea is we are interested in preserving these corals. So as part of global climate change, the acidity of the oceans is going up, and this is resulting in a bunch of coral bleaching events, which you may have heard of. And so one of the idea behind this project is that we have a bunch of these Western Pacific corals that are known to be, they're living in somewhat extreme conditions defined by chemistry. And so we think that they're probably resilient to these future climate conditions, and so they're good candidates for coral restoration. Another cool thing about these reefs is they're pretty interconnected with each other. And so that's kind of illustrated with these little arrows down here. And so this is from a different study that was looking at these connections between these coral reefs. And so you'll see that there's like a really large density of arrows along these coasts. And so these are kind of the connections on kind of a 40-day time scale. If you go to like 130 days, you see even more connections, and you're getting out pretty far out into the deep ocean. So that's the Galapagos. So the idea, high-level idea behind this project is if we can identify the portions of the coastline that are most effective at reaching other places, that's a good candidate for conservation. And so how do we determine these things? So one way is to run an ocean model, get out some flow fields. You can advect little particles in them. These particles represent coral larvae, and you see where those particles go, right? So if I see I deployed a particle on the coast here and it's moved all the way out here, well, maybe that's a good thing for our restoration project, right? So this is the kind of insight we're trying to get to. I'm not going to go that far today. Instead, we're at the first step of this project.
Yeah, that's very interesting. I'd love to know, and if this is totally out of scope, feel free to tell me, but how are these studies and the work you do fed into like decision making of what actually happens?
Yeah, so one of the lead scientists on this project, Joni Kleypas, who's at NCAR, is the bigger expert on that kind of thing. So this is kind of an exploratory internal NCAR project to see what we can come up with, and then we'll go to foundations, for example, and say, look, we've come up with these insights. Here, these are possible targets for conservation, and kind of work from there.
Great, very cool.
So it's kind of, that's the long-term goal, right?
Yeah,
and we're kind of 2 months into this thing, basically.
Awesome, cool. Let's jump in.
Yeah, so kind of at a high level, what happens is we run an ocean model. We save a lot of output. We kind of make sure it's sensible. Like I said, we use these flow fields to move things around. We assume these things look and behave like larvae, questionable assumptions. Step 3, question mark. Step 4, we do some science and we get to conservation and science papers. So we're at step 1, which is we've run a model and we have a bunch of output. And so how do we work with them? The answer is Xarray and Dask. So I've put here, we need scalable post-processing analysis software. And post-processing is just what people use for analyzing output that's come out from these models.
And let me ask how big in general these data sets are, and how long do these Fortran models usually take to run?
Ooh, they can take a while. This one was taking, I think it was 2 days for 1 year of simulation time. And our goal is to do 25 years of simulation.
Wow.
For this particular model. In terms of data size, I'll get to that. I actually typed that out somewhere.
Sounds good.
Okay, so we're going to talk about Xarray, and the key thing about Xarray is that it wraps other array packages like Dask array. And in wrapping it, what it does is adds a layer of metadata handling. And so that's what we'll see. We'll see, we won't be thinking just in terms of NumPy arrays or Dask arrays, but in terms of, here's a Dask array, but I also know all these metadata things, like this axis is time, this axis is latitude, that axis is longitude, instead of axes 0, 1, 2, right? So usually this is what I do. We are running on NCAR's cluster. So people call it HPC, so high performance computing. And usually I start, so we are on Casper, which is an associated cluster. It tends to have more memory. So here I usually do this. I use a project called Dask job queue, which, and here I'm calling slurm cluster. I give it a kind of things, tell it to run. So in this case, I already have 12 workers. I've done this so that we are not waiting in queue. So if you go to this pane, you'll see that I have 12 Dask workers all waiting for me to give them something to do. In the background, so here's a little command I run. So this is something I would run at a bash shell. It shows that I have 12 Dask workers running in the queue, and these are all their job IDs, et cetera, et cetera. So here you see Dask job queue is interacting with our cluster's scheduler, right? To give me resources that I've asked for. It's kind of fun. Okay, I got some imports. I'm going to create a little client, which is already there. And so we asked about data sets. And so the data looks like a large collection of netcdf files, which is basically a subset of HDF5, if you're familiar with that.
Yep.
We have basically 1 file per day, which represents a daily average of all our fields. And currently we look at 1 year of data, so that's 365 files. So with 2 GB per file, we're looking at 720 gigabytes on disk. And so this is a little directory. I'm just going to run ls. And so you see this is what it looks like. There's a bunch of files. It's 1 file per day. Has this .nc extension. That's a netcdf file. Oops, I seem to scroll too much. Okay, so the way we interact with the data is by using Xarray. So that's XR. And so in this case, I've told Xarray to open my data set is the first file. And I've told it to use chunks equals -1. So this is saying 1 chunk for the entire file. So this is what Dask array would expect. And what you'll see now is a cool HTML wrapper. I'm going to start by clicking here for data variables. And down here on θ0. So I'm going to start all the way down here, which is hopefully familiar to some of you. This is the HTML representation for a Dask array, right? So you have this array turns out to be 500 megabytes. It's got the shape. It's got 1 chunk. And this array, it represents seawater potential temperature with units degrees Celsius. So now you're starting to see the metadata that Xarray is layering on top of Dask array. Right? So this is Dask array. Here's a bunch of metadata. This Dask array, we can see its shape has 4 elements here. So that's a 4-dimensional array. And if you look up here, those are the names of those dimensions. So the first one is time, or axis 0 is time. Axis 1 is ZL, which would be depth. Axis 2 is YH, which you would think of as latitude. And axis 3 is XH, which you would think of as longitude. Right? So This is the first level of metadata that Xarray adds to use. It adds names for your axes. So instead of thinking in terms of axis 0 and 1, I think in terms of axis time and axis Z, axis Y. The second thing that it does is Xarray kind of generalizes what pandas brings to tabular data, which is it brings coordinate labels. So we know, for example, that this thing has XH and YH dimensions. So if I go up here and click, it tells me that my YH has values from -14 up to 29.975. So that's in degrees naught. So these are latitudes, right? So I know what point in coordinate space each of my Dask array values correspond to. And this metadata is all bundled up together in a little Xarray object. And so, at this point, it's just a lot of information that's being kind of encapsulated together, but it ends up being super convenient to use. So I'm going to type this out. So I'm going to look at temperature, so ds.theta-o. I'm going to pick up. So what I've done is indexed and pulled out the first element on the ZL dimension. So this would be the most surface layer. So if you looked at our metadata, you'll see that ZL is 1.25. So this is 1.25 meters below the surface of the water, right? So it's pretty close to the surface, not exact. And you see that basically underneath what's happened is Xarray has taken this and made it a Dask array indexing operation. So I've lost one dimension, right? Mm-hmm. And the cool thing about this is making a figure. This is something I do basically all of the time. And so I just run it. You see that a little task showed up for reading it and our little Dask dashboard. And so you see a really pretty image of sea surface temperature for this model. You'll see that, yeah. And so this is a matplotlib plot, right? So this is Xarray building on top of matplotlib and also Dask array. It's told Dask array to give it the actual value. So you see a little compute task there. And it's plotted up on screen. It's used all the metadata it knows to make a little nice labeled figure. So you see longitude, latitude. These values are dimensional values, right? So it's telling you that we are at, this is 260 degrees east. This is the equator at 0 degrees north. And this is temperature with these nice color bar and nice values.
This is awesome. So I'm a total Xarray noob. And so firstly, I've never used Xarray, but I understand all the code you showed, which means that there's a lot of great work that's being done into API design. And on top of that, you've written minimal code as well to start looking at your data. And that makes me feel good.
So like personal story, somewhere in the middle of 2017, I stumbled on Xarray. I was scrolling to the documentation. It was a little confusing. I got to the plotting page, scrolled down, and I was like, this is too easy. This is something I do 100 times a day. Yes, please. And so my first Xarray PR was actually to make it easy to plot my data set. It was great.
Awesome.
I was going to say, like, the plots didn't look this good in 2017, I don't think. There's been a lot of work over time.
Yeah. They were pretty close though. I was very impressed.
Cool.
Okay, so this, we've already done something. We've subsetted using, ZL instead of, axis 0 or something. The NumPy version of this would be a little more complicated, or Dask array version. So the nice thing I like about Xarray is that it lets you think in terms of your metadata, which you always have. Like nobody just has data. You always have data plus some metadata. This axis is time, and each point on this axis is these particular time instance. But the nice thing about Xarray and pandas is that you can use that knowledge, right? You don't have to remember what axis 0 was. So here's another illustration. So in this case, I am selecting in label space. So in this case, ZL equals slice 100. This is give me the first 100 meters, right? So this is in dimensions. I'm taking a mean along axis ZL. Again, I don't have to remember which axis 0, 1, 2, 3. I just do it over Z. And again, I call plot. So we'll run this. You see Dask is computing, and boom. Also another cool image. This is showing you that the equatorial Pacific tends to be kind of cold and it's a little warmer off. You see some cool vortex eddy features up there. It's pretty fun. But I think like Hugo, as you were saying earlier, this is pretty readable code, right? I can go through this 2 months from now and I'll know that I picked the first 100 meters, I took a mean, and then I plotted it. Great.
Yeah, and actually, I didn't say this before, but it like, and I slightly hesitate to say this, but it kind of looks like what I want my NumPy code to look like sometimes. As you say, like using the metadata that has to do with my mental model of what my data actually, like, it's in my head, right? So
yes, you definitely need Xarray then.
Awesome. Sold to the Australian on Zoom.
To the Australian. Yeah. Okay, so this is a little, it's also cool, a little more involved. So in this case, what I've done.
And I'll just say, Alexis has just commented, Alexis Kaminsky, that Deepak's plots look pretty good even back in 2017. So there you go.
It's because I was using Xarray. Okay, so the point here was, what was I doing? We were talking about broadcasting. This was also something I found kind of annoying. I used to use MATLAB, then I switched to using NumPy, then I switched to using Xarray. So here what I'm doing is basically I have my 4D data set, and say I want to know how different is my temperature from the surface value, right? Simple question. And so what it's doing is this is a 4D array and first, and that's a 3D array the second. And what it's done is taken the 3D array and expanded out in the fourth dimension, the Z dimension, appropriately. So again, in NumPy, you would usually do something like np.newAxis. I think even with Dask array, you would have to do something like that. Xarray will do this automatically because it knows that the ZL dimension is missing. It will add it in and do the sensible thing for you. So again, it's one more level of not having to think about what your data looks like. You just use the metadata to help yourself do these things. So that was, the quick demo of what Xarray does. Another cool thing about Xarray is that Xarray objects are Dask collections, thanks to some of Matt's great pull requests. So if you're used to Dask array, you can also use Xarray. So in this case, I've called dask.persist on a couple of variables just to save some kind of time. You'll see that it executed and it's loaded things into my distributed cluster memory. And now I can do my usual Xarray things. All my computations will be scattered across the cluster, et cetera, et cetera. Things work really well. I'm going to cancel it just to take it off. You could do things like visualize. And here you go. That's a Dask graph. So this, in this case, is showing that there's a file, there's an open dataset task, and that's going to give me my array. Right. So if you know Dask array, you can pretty easily upgrade to using Xarray. The same is true for NumPy. And I've talked about NumPy and Dask, but Xarray basically wraps at this point most ND array-like things. So there's been some work on wrapping sparse arrays. You could, in theory, do QPy and GPU arrays. I haven't actually experimented with it yet, but I would like to soon. There's been a lot of work recently on Pint. So this will allow you to add units and not worry about multiplying by all kinds of some kind of scaling factor. Then the code will just do it for you. So
that sounds great. We have a question in the chat from Juan. How does matplotlib deal with a non-X11 interface?
I put in the chat a link to the Matplotlib backend's documentation.
Yeah,
it's
a complicated question.
Oh,
Matplotlib is.
I haven't seen that in the chat, Matt. Just
Oh, well, that's concerning. Anyway, Matplotlib is going to be is a beast, an amazing, highly pragmatic beast. But
yeah,
I'm not gonna. I know how to answer that question. I'm gonna try to deflect that away from Deepak.
Okay. So, I've shown you kind of quickly what Xarray can do with a single file, and now we have 365 of these. And so here's where we start to really leverage Dask. And so what we're going to do is try and read all those 365 files in parallel. And this is kind of a common pattern with Dask delayed. I think there's a blog post on the Dask blog about this. But basically, here I have a list of file names, and you would loop over that and create a delayed thing. You call compute on that. This ends up giving you back a list of Xarray datasets, and then we combine these to form a giant dataset that represents all 720 gigabytes. So you'll see a bunch of tasks here. So that's Dask delayed running in parallel. So it's gone, touched all 365 files, read just the metadata, not the actual data, just the metadata, and created a representation of that data set on disk. So here again, you have a little Xarray wrapper. You'll see that time 365, that's 1 per file, right? So it's gone through all of those. And it stitched them all together. So let's look at our temperature Dask array again. So this thing is a total of approximately 200 gigabytes. That's the shape. And it's chunked like so. I've asked it to add some chunks along the last dimension here. So I thought this is really great. It's using Dask delay to create a bunch of Dask arrays that and that gets wrapped by X arrays, and then you combine all those together till you get this big thing. And then all the cool stuff that I showed earlier basically just works. So here, for example, a common thing to calculate is something like, what is the monthly mean sea surface temperature? It's simple calculation. And here's how you would express that in Xarray, right? So I pick ds.theta, that's the temperature. I pick the surface level, just as I did earlier with iCell. And then I use resample time equals m dot mean. So if you've used pandas, this should look exactly the same, because Xarray tries to do that. So, this is a kind of complicated operation. It has to go through, figure out which months, which time steps correspond to a particular month, et cetera, et cetera. And see, we get back a little Dask thing again. So this is an Xarray object that wraps a Dask array. You'll see time is 12. So there are 12 points on the time dimension, 1 per month. All kinds of cool stuff. But at this point, it's all lazy because we're wrapping Dask arrays, right? So everything's lazy until you actually ask for a value. So I'm going to do that here with, again, the dot plot. What we're going to do is create a bunch of subplots so that there are 3 subplots per row, and some matplotlib stuff. So I'm just going to run it. You'll see it shows up. Dask is computing, and now matplotlib is thinking about making me a figure. Okay, there it is. So this is basically 1 panel per month. Each panel is the monthly mean sea surface temperature. And you can see as you go through this, if you focus at the equator, it's kind of warm on top, and down here it's kind of cool. That happens to do with the winds getting a little more intense during the summer, and ends up cooling the sea surface.
And can I ask, to generate these plots, did we just process the entire 700 plus gig data set?
No, so this is just one variable. So it's only been, and it's only one.
Or this is, okay, yeah.
It's only one level even.
Okay.
So this is kind of common, right? So it's kind of common to say, yes, I have this huge data set, but very rarely am I actually using the whole thing, right? So to me, I commonly end up slicing. In this case, I've sliced out just the surface level, right? So that's a huge reduction right there in how much data we're processing. And then I do more complicated things.
Right.
But yeah. So yeah, the things that I do, I tend to, I tend to load a representation of a big thing and then reduce it down to a small thing and then look at that for details. And then once I see something interesting, I may go back and then compute something on the whole thing, right? But for now, this is how I do a lot
of Xarray, which gives you the expressibility to
Yeah.
select the things you want, and the beauty of laziness, which allows you to think about having the whole thing in memory, but only actually work with the bits that you need.
Exactly. And so that's the cool thing about combining Dask and Xarray. So you get the laziness, but also the kind of composing expressiveness, readable code that goes along with it. So I had this bit about comparing to some satellite observations, but I'm going to skip so that we see a little more fun, a little more complicated stuff. So let's scroll all the way down.
Number time.
Number time.
Special guest, cameo. Cool.
I just think this is so great. This is just, I don't know. Okay, so we're talking about the ocean, right? And a thing about the ocean is we like to think about density. So the density of water, it's approximately 1,000 kilograms per meter cube, but it changes enough, somewhere in the 5 to 10 range. That's important for ocean physics. So a common thing that we want to calculate is the density of water. It's a function of salinity and temperature, so and pressure. In this case, I'm going to skip the science. We're calculating a special kind of density called potential density. But from a computational perspective, this is, there's a bunch of crazy constants. There's a bunch of additions, multiplications. We have power 2, power 3. It's kind of complicated task. This is actually a really simple equation of state for the water column. It's what's used in this model, so it's sort of computationally efficient. I think the current state-of-the-art one is 75 terms that is empirically determined and has all kinds of crazy stuff in it. So it can be a pretty expensive computation to run. So this is the simple one. So this is a little nice function. And so the kind of high-level concept here is that we use Xarray things, and it's kind of convenient when you use Xarray's built-in functions like mean that I showed you, or resample, because you have an Xarray thing, you call this function, and you get back an Xarray thing. But a lot of us have analysis code that expects a NumPy thing, or maybe it expects a Dask thing, right? So you can't always give it an Xarray thing and just expect it to work. In this case, it would, but I'm trying to illustrate a different point. And so what's nice is there's like multiple levels of abstraction you can build down here. So there's a function that's called Xarray's apply ufunc. It's kind of ignore the name, but here are what the arguments are. I give it a function. Let's say it expects just NumPy or Dask arrays. In this case, it expects NumPy arrays. I'm telling it here's a salinity. So this is a data array. I should put a little comment here. So this is an Xarray thing. Temperature is an Xarray thing. And so here's where Dask comes in. I can say Dask equals parallelized. And what this does is in the background, it will automatically parallelize using Dask's apply goofunc or blockwise, depending on which version of Xarray you have. And then there's some extra info. So what's cool about this is you can take a function that didn't know about Dask. It didn't know you had to be lazy. It didn't know you had to be careful about how you wrote it. So things stayed lazy. You can apply it on your Xarray things, and with just basically this one line, like 90% of cases, this will just work. It will automatically do the lazy parallelization for you. And so I can illustrate that. I'll run this little cell. And here I'm going to run the compute, and you'll see it distribute, and we'll just look at the time, right? So it's running, you see EOS is here, that's my function. It's calculating density, it takes a bit. But you can see that it's distributed with Dask. And it's all happened because of this magic line. So that thing took 12 seconds. And this thing's not useful anymore. Sorry.
So Deepak, there's a question in the chat from Joseph Berry. The question is, how many threads should you have per worker for such a computation? I noticed that when you started up, every worker just had one core, but had like quite a bit of memory. You've chosen to have a relatively high memory, low CPU mixture here.
Yep.
Why? And do you still want that with the computation? How do you make those decisions?
I have chosen to make this decision because I've learned the hard way that HDF5 is effectively single-threaded, and my netcdf4 files are basically HDF5 files, so they end up blocking. So if you had an all-threaded job, it's basically pointless. And so what I have chosen to do is, for most things that I do, disk reads are the slowest bit. And so by choosing multiple processes, I basically parallelize across all of that without having to worry about things. That was my thing, yeah.
But you could have been using this also on Cheyenne or something, some machine that had more CPUs
Yes.
per gigabyte memory. Like you're really heavily optimizing, I'm guessing, for I/O and for storage, and less for computation.
Correct. I do that too sometimes. So there's sometimes when I would just take a single node in Cheyenne, which is 36 cores and 100 gigs. So if I had a low memory but high computation workload, I would do that. And I think I usually do 9 processes. Okay. And yeah, but I usually set, I ask Numba to use 3 threads or 4 threads. So it's 9 Dask processes, but 4 Numba threads. And so it just zooms through everything on that. So yeah, it depends on what you're doing, I guess.
What I'm hearing is the answer is that it's complicated.
Yeah, it's trial and error. Okay, so we did this computation. It took 12 seconds, right? So I'm going to go up and uncomment exactly 2 lines. What this does, it uses the great Numba project to compile this function down to, I don't know, it compiles this. So you end up running this complicated computation in in compiled code, which makes it really quick. So we'll, oops, anyway, this is taking so long. So once this function has redone and figured out its Dask graph, we'll retime it, and you'll see there'll be a factor of 4 speed up. Okay, so now with Numba, I don't know why this is suddenly become slow, but you'll see that it should take about like 3 seconds or something to run. There you go, 2.52 seconds. So that was a factor of 4 speed up by adding 2 lines, which told Numba to compile the thing down. And it works with Dask, and it also works with Xarray. This is like, to me, the high point of the data ecosystem here.
Yeah, it's great that these 3 projects, which are pretty independent, all work together pretty seamlessly. There's another question from Guy Mascal. What about scikit-learn? So I'm guessing sort of, let's take a look at apply ufunc or other ways of applying sort of non-Dask functions on these large data sets held by Xarray. If you wanted to use some scikit-learn function, is that possible?
I think so. I don't know about scikit-learn specifically, but the point of this kind of approach, which is apply ufunc, Dask parallelized, is this is anything that expects a NumPy array. There's really no limitation as far as I know. Would you agree, Matt?
Sure, to some extent. I mean,
to some extent. Yeah.
There are always counterexamples, but yes, generally yes. It's nice things like apply ufunc, map blocks, blockwise. Those are all designed to take the existing functions that are designed for single NumPy arrays or single dependent data frames, and apply them in parallel across lots of data.
Yeah.
But your algorithm may be different. If you're trying to do random forests, that might be okay. If you're trying to do gradient boosted trees, it might not be okay. Finally, a question from Thomas Moore. I'm going to hope that you understand the question, because I don't. Is there any work on a Numba version of GSW toolbox?
Ooh. Okay, so the background behind that question is, I remember I was talking about a very complicated equation of state with 75 terms. GSW is a package that applies that. So very recently, I think there's a Pythonized version or like a C extension version of that. So I don't know that so I don't know that there's a Numba version of it, but there's a C version which should be pretty quick and a lot quicker than the current one. And you can apply it with apply ufunc and Dask parallelized, and things will work.
Great.
Okay. So this next little demo is another Numba demo, but slightly more complicated, but very relevant to oceanography in specifically. So here, for example, I've calculated potential density, right? So I got this big array, and I'm just going to run this. This will be kind of quick. So now what we're looking at is, this is a profile of density in the ocean. So, oops, let me scroll down. The x-axis is density. It's going, like I said, it's approximately 1,000 kilogram per meter cubed. We're looking at top 200 meters. And you see this thing has a nice shape to it, right? It's kind of low density, lighter waters up near the surface, high density, heavier waters near the bottom. And this horizontal line here is a little calculation I've run, which I'll get to. But what it's doing is trying to pick up this little kind of curvature. It's where you go from being basically vertical to a little more slanted, right? And there are many ways of doing this. This is, this upper layer of the ocean is called the mixed layer. And everyone has their favorite algorithm for finding the base of the mixed layer. But at the high level computation perspective, this is what you want to do, is you want to go through every point in latitude, longitude, and time. And so you have just this little vertical profile, as you see here, and then you want to search for, the base of this mixed layer. There are other such quantities that you may want to look for, but the kind of basic concept is that the vertical dimension in the oceans is special, and it's special because it's tiny. It's at its deepest, the ocean is 5 kilometers deep, but it's hundreds or thousands of kilometers wide, right? So it's like the ocean is a really thin layer of fluid on the Earth's surface. This makes since that combined with the Earth rotating makes the vertical dimension kind of special. So we commonly have to do things that are basically at every that long point, do some operation. So this is, again, to me, a big achievement of PyData ecosystem is I can do something like this really quickly and in a very performant manner. What I'm going to apply is this, in this ETPack module, I have a little function called HMXL, and that's what it's calculated and plotted. You can see here I've used dask.compute because Xarray things are basically Dask things, which is kind of nice. And so this is the kind of thing that before, in my MATLAB days, I would write 3 for loops, one over latitude, one over longitude, one over time, and then I would solve this problem. So here is a kind of complicated function. So calc HMXL is here. This is in a little separate Python file. And so you can see, again, the same pattern. There's apply ufunc. There's a function that's been applied. It gets a bunch of inputs, and I say Dask is parallelized. And here's what that actual function is. So I want to start looking at this bit. So this is code that would be the innermost loop of my computation. Right, so it's going through, it's calculating a bunch of things. It's got a bunch of if conditions. It's basically searching right through this profile. And I want to do this at every point. And if I was to for loop over the 200 gigs of data that I have, it's going to take an incredible amount of time. And so here again, I'm using a Numba function called goVectorize. What this is basically telling you is I expect to get a one-dimensional vector. I get another one-dimensional vector. I do some magic computation, and it gets back one number. So for understanding, this first one's going to be the density profile that you were looking at. The second is going to be the depths at which you know the density. And the last one's going to be the mixed layer depths. So to make that clear, what I'm giving the function is this little profile. I give it the little depths at which I know these points, and it gives me back this little line. Right? It gives me back the value 75 or whatever. It's a little complicated, but because I have Dask and Numba, I can do this. So I'm asking you to calculate the mixed layer depth or any other fast number calculation. So it's going to do the whole thing in compiled code. It's going to resample to get the monthly mean. I'm just picking January and I'm going to plot it, right? So you see here, this little transpose task is that Numba computation that's happening really quickly. It's distributing across my 12 workers on Casper. And it's just doing it. So this is a slightly more complicated version of our previous example, right? But it's a really common thing in oceanography that you have to calculate something. The most obvious way to do this thing is to for loop through every point, which would be really slow in normal Python. But 4 lines of code later, it's compiled. And with Dask, it's distributed, which is great. So here's
there's an amazing amount of complex orchestration that just happened when you pressed Shift Enter. Right? We spun up some LLVM compilers. We talked a bunch of machines. We wrote some some actual oceanography stuff down there. It was 5 or 6 PhD theses all just got referenced, I think.
But this is, I don't know. To me, that is the coolest thing, right? It's somehow all of this kind of works, and I don't have to know all those details. I don't have to know that LLVM is doing something. I just need to know how to give it that information. Here's the information.
I was laughing a little bit when you said Numba compiles to something. You kind of drifted past that thing, which is great.
What does it compile to? Is it assembly? I don't know. No, machine code?
LLVM, which then does whatever LLVM does, which is some sort of machine operations, sure. But
okay,
that's another set of theses we don't need to think about. We got a pretty picture though. Look at that, pretty picture.
Pretty picture. So there's still some bugs in this code. All the oceanographers are going to be so you can see this little speckling. So something's definitely gone wrong. I haven't fully debugged it, but complicated number function, compiled code, distributed application, distributed data set. I should say the other cool thing that's happened here is there are all these open data set tasks. So the data has stayed on disk until I've actually asked for it. Right? So when I hit Control Enter, it's read the data, Dask does its thing, gives me a value, then it reads the next thing, and so on and so forth. So you don't end up using too much memory. All right, so that was kind of apply ufunc. So this last bit is kind of my favorite bit of Dask. And there's kind of a little backstory here about at a Pangeo meeting a year ago, I basically walked up to Matt and said, hey, do you think it's possible to write a version of Dask map blocks, but that uses Xarray objects? And so the idea behind this is, I have my Xarray thing and I have all my metadata, and I'm really used to writing Xarray code. But sometimes it really just makes sense to write a thing that looks like a for loop, but that tends to be slow, and it could be annoying to write it in Numba, just because then you have to forget about all your metadata and you're back to your old NumPy way of doing things. And so the idea was that, let's say you have a function here. It takes one argument, which is an Xarray thing, and I want to apply this in parallel, right? So I want my function to get Xarray things so I can do Xarray operations, with the convenience of Xarray, and send back something else. And the Dask version of this is called map blocks, which is given a block of a Dask array, apply a function, get its result, send it back as a Dask array. So this is the world's most simplest plotting function. All it does is calls .plot, which is kind of similar to what I did. But this could be any complicated Xarray map.lib code. It could also be pandas code. So I know Joe Heyman, for example, who Matt, basically does this in here. He calls two data frame, gets into pandas and does something with the pandas. The whole pandas ecosystem is suddenly available for you to work with in a parallelized distributed way. Okay, so what I'm going to do is, so I'm going to comment out this little plot line so you can just see that what it's doing is making a figure. So it's made a very simple figure. I'm going to close that figure just so we don't run into issues. And oh, I forgot to clean this up. So what it's doing is it's going to make a figure, it's going to save it to file, and then it's going to close the figure handle, and all it's doing is returning .time because it needs to return something. I forgot to clean up my directory, so I'll do that maybe quickly, or maybe not. Is there a way I can call RM here? I guess I can do this.
Bang, exclamation point.
That's
or,
right.
Great.
Yeah, I think this works. Star.png. Okay, so I've just emptied out a little directory. So we can clearly see that stuff is going to happen. Okay, so there's nothing there except a little directory. And so what I'm going to do here is map blocks. And so what I want is to make a bunch of these images in parallel. This kind of one thing that I like to do in my presentations is to show videos because we can. This is the advantage of doing ocean modeling is you have cool videos of basically any quantity that you can see or think of computing. And it's really nice for illustrating things because humans like to look at things. And so here what I'm going to do is I take my sea surface temperature, I'm going to chunk it so that you have one chunk per time and one chunk size per lat and lon. So what this is doing is basically you end up with 365 blocks, one per time step, because I want to look at one time step at a time, right? So this is a function that only makes sense if you have all of one time step with you. And I'm going to call .mapBlocks plot, which is that function up there. And this thing is lazy. And so here what you'll see is I have called visualize so we can look at the graph. And so the reason I wanted to show this off is I just think this is a cool use of Dask, right? So here is a file. This is the graph where it reads up as 3 chunks. It's brought it back together because I asked them chunk those together so you get one block per time. And then this is a little Dask array thing. But now what's happened here is there's 4 other tasks. These are basically time, X, Y, and Z that are being passed into this function. They get wrapped up into a little Xarray thing. Then they go to a plot function that we wrote up there. And this is the result of that computation. So up to now, everything that we've seen is Xarray just adding a little layer on top of Dask array. Right? So when I call Xarray.mean, it ends up calling Dask array.mean. But here, we've taken a Dask array, but we're also using Dask capability of being just like a general task execution framework. So we create little tasks to create a little data array in there and all the necessary metadata that was associated with this. Yeah, so anyway, this is a really, to me, a really cool application of Dask and Xarray. And we've written up, it's all wrapped up in this little map blocks thing. So going back to that scikit-learn function, I think scikit-learn expects NumPy arrays, but maybe you have some other function that works really well with Xarray things, and you don't want to spend the time in converting that to a pure NumPy thing. Well, you can use map blocks and benefit from parallelization really quickly.
What I'm hearing you say a lot of is that Xarray is solving the 95% use case for oceanography. Yeah. But sometimes you need to go outside of what Xarray offers. And there are options for that. You can be more flexible, you can do more custom things without really leaving the world too much. There's an escape.
Exactly. And it's, for me, it is literally very hard for me to write NumPy code anymore. I am just so used to using all this metadata that map blocks is just great.
Great.
Okay.
I think you're totally correct, Deepak, in that scikit-learn does expect NumPy arrays, and Matt spoke to different algorithms being able to deal with streaming data in a variety of ways. And I put this in the chat, something to look at as well for algorithms that can deal with large data sets is Dask ML. Also,
I think there is an open pull request on scikit-learn that allows them to use pandas and Xarray things. Wow. It hasn't been merged yet, but I've subscribed. Yeah. It's long.
That's a aspirational pull request. That's like a multi-year scikit-learn. People don't expect that to close next week.
But yeah, so if you wanted to use a pandas function, you can convert your Xarray thing, but maybe sometimes it's just easy to do this in this map blocks way. Sometimes things, you just need something that makes it easy. Okay, so an unfortunate thing is I found that there was a bug, which meant that this will not execute right now. So instead I'm going, there are bugs. So instead I'm just going to open this little local cluster thing. It's 40198. I promise I will I will make a minimal example and post it somewhere.
That is why I love you, Deepak.
Okay, so all I've done now is create a little local cluster. I've told it to use just 4 processes. It's tiny. It doesn't really matter. And I'm going to call, persist actually, so that we can actually look at what happens. Yeah. Okay, so this is mapped is an Xarray thing, just to make that clear. But because the integration with Dask is seamless, I can call .persist, and I can also tell it to use the local cluster, which is something that you would do with Dask array. And so I'll run it, hopefully oh yeah, here you go. So things should be running slowly, there it is.
So it seems like things are working on your HPC machine, but fortunately you're able to switch out. You have 2 separate clusters running, one on the HPC machine and one that's local, just I'm guessing on your login node. And you're able to sort of switch out midstream for the local one because something broke.
Yep, something broke. So here you can see it's writing files in parallel. I'm rendering to disk. So yeah, I'm just rerunning it and you'll see slowly it's increasing. So this is really cool. This to me was holy grail. So easy.
And so now you can make movies and share them in presentations.
I can make movies and share them, and they're very effective. Yeah, so it's just going, right? And this is really the most simple plot. I could make the most complicated thing and it would be distributed, parallel, and quick. It's just everything coming together. Also, I think the question about parallelizing matplotlib is pretty common. And here's an easy way to do it with Dask and Xarray if you really wanted. So that's basically what I had. I think we did somehow really well on time.
Yeah,
we did incredibly well.
I want to add one more thing if I can. So you mentioned there's some backstory to the map blocks function. You made it after we sort of talked at a Pangeo meeting. After you came to me, we then together went to the Nupari team. So people don't know, Nupari is an image viewer application that's also built on Dask and Xarray, but not used in the geophysical sciences. They're used a lot in sort of the biological imaging space. If people are interested in that, we actually did a similar talk with them couple of weeks ago. It was great. They have, also have great pictures, just a different kind. And I put a link to that in the chat if people are interested. So yeah, if you want more Xarray, but in a very different domain, that's a fun thing to go check out.
And building on that, I actually have a question which may have been discussed earlier on in this stream while I was writing some comments in the chat. So forgive me if this has been discussed before. How did Dask and Xarray first become coupled?
This is a great story. Matt should tell it.
I mean, it's not great of a story, but so relatively early on so Dask and Xarray both were created independently. And then, so Stefan Hoyer was sort of the grandfather of Xarray. He and I lived sort of close to each other in California. Stefan took like a week or two off of his work. He was working at Climate Corporation at the time. And so we worked together for a week or two and made the code bases work together. And there was some engineering stuff that happened there, mostly stuff that Stefan was doing. But after that, things were done. And that kind of changed, I think, fundamentally how Xarray was used or how Dask was used. I'll say that probably about half of Dask Array use today is through Xarray. Xarray was the first major project to adopt Dask, and it has definitely strongly impacted how it has evolved. So yeah, and ever since then, there's been great collaboration between the two groups.
Awesome, thank you. And as you started to tell that story, I actually remembered you wrote that story in a blog post on the history of Dask, or a brief history
I assume you already knew that, Hugo, and just prompting it.
Yeah, no, it was, I mean, it's still, we started at 7 a.m. local time for me, so things flood back occasionally. But I mean, Matt may blush, but I think this is actually a really nice blog post on the history of Dask and how it works in the general PyData ecosystem. So definitely feel free to check that out if interested. Let's wrap up soonish. I'd like to thank everyone for joining once again and all the great interaction in the chat. I'm wondering, Deepak, for people who want to get started with Xarray, what's a good way to do that? And then maybe for all of your oceanographer pals and other people who may be more experienced with Xarray, what can they do to push even further?
So the first part of your question, I would go to, this is our main documentation page. I like examples. It's just a quick way to see everything. We actually have tutorials somewhere.
I think we're also planning a Dask and Xarray online tutorial. People are interested. If you track the Dask Dev Twitter account, we'll announce it there. I think Anderson, who's in the chat on the YouTube live stream, is planning to present, maybe with help from Deepak. Who knows?
Yeah, I think I signed up there.
Great. But yeah, if people are interested, that's also a great way to follow up.
But if you're looking for some simpler material, here's one I did recently, which is Xarray in 45 minutes.
Oh, cool.
Simple. You can launch it on Binder, so that's pretty cool. I don't know, for the oceanographers, there's many ways you can go. I guess I would start at Pangeo, which is a project that's looking to put. Okay, so all the things that I've shown you today are really just possible because of the Pangeo project. So it's both trying to do things in the cloud, but also in HPC, but kind of linking Xarray and Dask, plus a whole bunch of other stuff like intake, Xarray, too many to count. Basically bringing all these packages together, making them work well together so that, scientists should be thinking about science and just a little bit about coding. To get that science done. So I would go here and start clicking around. There's a nice little discourse forum where you can ask questions and somebody will comment and try and help you. Yeah.
Fantastic.
Pangeo project.
And that statement, scientists should be thinking about and working on science and doing, the coding that they need to in order to do that, I think is a wonderful message to wrap up on as well.
If I can, so I want to close things out. I want to try and experiment after this. So I love these sessions. We get to, the three of us get to talk a bunch, and there's a nice conversation in the chat. I'm trying to find some way where everyone in the chat can engage together as well. Hugo, I apologize for not mentioning this earlier. I meant to bring it up. I'm curious in trying. I found a website, gather.town, which does like a combination video game / chat system. It's hilarious. We tried it at Coil for like a company meeting. It was a lot of fun. So people are interested, we can try this out. And it's really hard to have conversations with 50 people live. Gather Town combines like a little video game UI with video chatting. So if you walk around, you're next to people, you can talk to them. So I'm going to put a link in the chat. And if
I just have.
I'm going to put a different link in the chat.
Okay.
A specific space.
Yes, it will be the space that we're going to. Great.
And if you want to go there afterwards, it'd be fun to see people. Or if not, see you guys around.
So yeah, hope to see you in Gathertown. And thank you, Deepak, once again.
Yeah, thanks for having me. This is a lot of fun.
For us too. Well, for me too. But I think I can speak on behalf of Matt. All right. So we're going to stop live